Hey everyone, this is Tia Yusuf, and in this video we are going to be discussing AC circuits. The two things that I want to focus on in this video is going to be understanding impedances and also understanding the phase differences. And by understanding both of these functions of a sine wave and of these AC components, we're going to be able to easily differentiate between different signals. Here is an example of an AC voltage source, and we'll be given a lot of parameters as to what it's outputting into our circuit. They might give us a value and then tell if it's peak or peak to peak, and they might give us a frequency value that will go into our omega. Same can be true about our AC current source. And like I was saying earlier, I want to really focus on this theta at the end here in our function for voltage and current, and I want to focus on this impedance. So impedance can be described as the opposition towards current flow in our AC circuit. In DC, we only had resistors, or if we had another component like an inductor and capacitor, we looked at transients. Here I want to know about the total reactance, how all my components react to my circuit, so those frequency-dependent components, and also that total resistance. I'm going to go over a couple of examples, including a resistance circuit, a RC circuit, and an RL circuit. This is our first AC circuit example, and this is going to be a simulation. And what we want to answer with this simulation is, what is happening in our AC circuit? So here we have an example of an AC voltage source. If I go right here, I can see the different attributes that are tied to this AC voltage source. Remember, in DC, the only real parameter we had was that voltage value. So if it said 10 volts, it would output a total of 10 volts, or if it was a current source, it output a total of 20 milliamps, or whatever the value was set to. Here we have different options and parameters that can change what our sine wave input looks like. So our sine wave input has a 5 volts amplitude. That means it goes from 0 to 5 volts and also 0 to negative 5 volts. When we go to simulate this circuit, we will see that current's going both in the forward or clockwise direction and the backwards or counterclockwise direction. That's what AC is talking about, the alternating current. The other parameter that we have here is frequency, and that's measured in hertz or cycles per second. That determines how many times I'm going from 5 to 0, 0 to negative 5 in a second. So 400 hertz isn't that fast of a frequency, but it will let us see a lot in our circuit. And we also have a phase angle. Here we just set it as 0 degrees. When I go to simulate my circuit, this blue sine wave represents our circuit. It represents that input sinusoid that we put in. And then we can see these orange or these green boxes going back and forth. That's representing our current. So our current is going clockwise, then counterclockwise. And it's repeating that on and on and on. And just to show, we can see as I increase frequency, it is going back and forth more rapidly. And that's what we see when we have a higher frequency. I'm going to move it back to that lower frequency so we can see our sine wave. So now I want to see, what does my waveform look like for the current at my resistor and the voltage at my resistor. So I'm going to highlight this. I want to say show waveform. And I'm also going to look at this voltage waveform as well. Okay? So now on my graph, I can see, now I have two sine waves. The blue represents the current through the resistor. This also means the current through the entire circuit, and that's because it's one series circuit and there's only one component in there. And then my green wave is the voltage across the resistor. I instantly drop 5 volts across the resistor and then go to ground, and that's a 5 volt variation. So like I said, we can stop this and look at one cycle. If I want to look, I'm going to do here to here, and this is one cycle. And what we see here, looking at this one cycle that's 2.5 milliseconds long, I start at zero, nearly zero, for my voltage. I can go up to my maximum. I go back down to zero, back to my minimum, and then back to 0 volts across, or 0 amperage across. I see that my blue and green wave, when they're overlapped like each other, I see that they're in phase. They reach their prominent peaks at the same time. They touch 0 at the same time. And so there's no phase difference between the two. There is 0-degree phase difference between the two. Neither is leading or ahead. They are in phase with each other. The last thing I want to highlight about this simulation is, if I wanted to describe how my resistor was opposing or resisting this current that's going through it, I can just describe it with its ohm amount, with its resistance amount, 1 kilo ohm. That's because at the resistor, they are in phase. So this is our second example of our AC circuit, and this is an example of an RC circuit in AC. Just like before, we have a voltage source, AC voltage source at 1 kilohertz. And we also have the same 1 kilo ohm resistor. We also have this 50 microfarad capacitor. And what we want to see is, how is this capacitor reacting to the circuit? What does its voltage value look like? What does its current look like? And just like before, what we can expect before we do the simulation, we can expect the current going forward and then backward. It's alternating clockwise and counterclockwise. We should also expect for that resistor to be in phase with itself. The voltage at the resistor and the current with the resistor should be in phase. So let's run this simulation. So we see once again this blue sine wave is our input signal. We see it goes across this resistor. We drop a little bit of voltage, and then we even have this alternating current at our capacitor. And our capacitor is switching polarity, plus, minus, plus, and minus. We also have 2 voltmeters that are going to help us analyze our circuit more closely as well. So if I reset my waveform, and now I want to look at the voltage and current at my resistor, I will see, just like before when they were in phase, my voltage and my current at my resistor are in phase. They're reaching that amplitude, that maximum value at the same point. They're reaching that minimum at the same point. I also know that the current at the resistor is the current at the capacitor. And that's because they are in a series circuit. That series idea still applies. There's one continuous path flow. The current at resistor is the same as the current at the capacitor. This is one continuous current flow. I'm going to reset my waveform one more time and just add the current through the capacitor. And we can see that voltage is the same. And when we put it all together, we see all of them overlapping. So my orange current is overlapping my blue current, and that voltage value is similar enough. We have different axes set. But we can see that the current at the capacitor and resistor are the same, and that the voltage of the resistor and the current of the resistor are in phase with each other. Now what I want to look at is, what about the voltage of the capacitor? Is that also in phase? And I can think back to transients when we were working with our capacitor and inductor then. For a capacitor, it takes time for that charge to accumulate across the 2 plates. So I actually want to expect the voltage maybe taking some more time to go into effect. So now my orange is my current through the capacitor, and then blue is my voltage coming from the voltmeter. And I can see if I'm just looking at one cycle here, one cycle is about roughly 1 millisecond. I started at 0 for my current and my voltage. I went up to my maximum. This is my maximum for my current. And I reached my maximum for my current before my voltage value. And I see that happens again with this 0 point and also with this minimum. This is telling me that for my entire circuit, this current is ahead of this voltage value. I can look at any cycle, whether it's at any 2 points that are similar, no matter where they start and where they end, and I can see that my current is ahead of my voltage, and it's going to be ahead by 90 degrees, and that's for my capacitor. Here we are now going to do a quick summary of what we just saw in that simulation, and we're going to relate it back to the schematic. What we saw was in a circuit with our R and C that the voltage total and I total can have different angles. So our voltage peak started at 0, but our I total is based off of that total impedance that we see in our circuit. We also saw that VR1 and IR1, so the voltage sine wave and the current sine wave for our resistor, will have the same angle. They are in phase with each other. The third thing that we saw was that the capacitor, the voltage and current were out of phase. This relates to how we describe the impedance for a capacitor. I know always for a capacitor, if I was comparing the voltage of it to the current, that these angles theta 2 and theta 1 will equal a difference of 90 degrees. And so when I'm thinking about V over I as a ratio, those two vectors as a ratio, I can get to my description of Z, so that total opposition to current. And if theta 1 is always 90 degrees less than theta 2, what I have here is for my impedance of my capacitor, I can represent it as a negative 90 degrees. And that's describing that current leading the voltage or the voltage lagging the current. This is our third example of an AC circuit, and it's very similar to the previous one, except instead of a capacitor, we have an inductor in our circuit. Before we start simulating, we know, once again, we're working with this AC voltage source. This current is going to go forward and then backwards, or clockwise and then counterclockwise. And we know that also, if we want to see the waveforms for our if we want to see the voltages for our resistor and the current for our resistor, we should expect them to be in phase. So let's start simulating that. We can see if I separate them, the voltage and that current at the resistor are in phase. They're reaching the max and the minimums at the same time. They're operating at that same period. And just like before, we still see this input of a sine wave going at 1 kilohertz and then a drop across this resistor. So now let's try looking at the current of the inductor. We are noticing here that also for our inductor, that current is the same as that resistor. And that's because, once again, this is an RL circuit. They are in series with each other. The current should be the same. And now the last form that I want to look at is going to be the voltage across the inductor. And I want to see, is that in phase with everything else? And I can once again think about transients from before. That voltage across the inductor could spike, but that current could not. That current had to take time to go through the coils of the inductor to generate that magnetic field. So I'm going to expect my current to be behind my voltage for my inductor. So when I go to simulate, I have my orange is my current, my blue is my voltage value. I can pause it for a second and I can look at one full cycle. One of the cool things about this simulation is I see this little curvature here of this inductor. So that's my voltage. I see I had that sharp rise. And now I start getting to my sine wave, very similar to a steady state. I reached my maximum for my voltage before my maximum for my current. I see that looking at one cycle finishes before the current does as well. So I know, similar to the capacitor, there is a phase difference when I'm looking at the voltage of an inductor and the current of an inductor. My inductor current is lagging. It is behind my voltage. And I can see when I simulate again that this will keep on going forever and forever. Here is now our schematic recap of that simulation. Once again, this voltage from the source and the current, total current, can have different angles, and that's because that is based off of the impedance. So my equation, this Z total, can change and dictate whatever angle I have for the theta angle for my current. We know that even in my RL circuit, the voltage of my resistor R1 and IR1, so my current as well, they're in phase and they'll have the same angle. And this is why when I'm writing an impedance of the resistor, we're describing it as 0 degrees. So we can really ignore that part and just use that resistance value. For our inductor, we saw that theta 1 and theta 2, so the voltage of my inductor was 90 degrees ahead of my current. So that means theta 1 minus theta 2 will always have a difference of 90 degrees. And if I want to go back to this ratio of V over I see that for my impedance, I will now have an angle of a positive 90 degrees difference. And this will always be true. So I can use this in my equations. It can help me decipher a problem where I'm given a sine wave. If I was given a voltage and a current, I can see the difference in the x-axis, and it can maybe help me determine what kind of circuit am I looking at, which signals am I looking at. What we just learned with the capacitor and inductor can be described with our acronym Eli, the ice puppies. So I wrote them in the reverse order, but ice is actually going to refer to capacitor. And we're looking at what we usually use to represent our current and voltage. So our voltage in this case is getting represented by EMF, or you can say energy source, whatever you want to describe it as. And it's saying our current leads our voltage in the capacitor. And then for Eli, it's talking about the inductor. And it's saying that the voltage leads the current at an inductor. And that is also by 90 degrees. Hopefully that helps clarify what is the same between signals and AC, what is the same in the phase angles between each signal, whether it's the voltage of the resistor, voltage of the entire circuit, or voltage of a reactive component. We should be able to decipher them more easily and now be able to analyze them and use the right angles when we do our calculations. Thank you.